Thanks, guys, and especially thank you, Avian, for the lovely introduction. So I'm here today to talk to you about the work that I do in the chronic lung disease, emphysema. But before I start, I want to first introduce this man here. So for those of you who don't know, this is Lance Armstrong. And he was a professional cyclist who won 7 consecutive Tour de France medals from 1999 up until 2005, before he was caught of cheating. So basically, he was taking a number of sports performance-enhancing drugs in order to win these Tour de France medals. And one of the drugs that he admitted to taking was erythropoietin, or just simply EPO. And I'm here today to talk to you about the work that I do using a drug that is based off of EPO and seeing if it could be a potential new cure for emphysema. Clicker. But before I begin, we first need to understand exactly how the lungs work. So as you take a deep breath in, air travels through your nose or through your mouth and makes its way down your windpipe, which is also known as your trachea. It then makes its way down a series of smaller tubes until eventually it reaches the end air sacs, which are known as alveoli. Now, alveoli can be compared to a bunch of grapes. So the air is contained within the grape itself, and then on the outside, where the flesh is, are a number of tiny, tiny blood vessels, which are known as capillaries. And this is where the exchange of gases occurs. So if we were to look more in detail at one of these alveolar tissue, or these alveoli or grapes, this is what you'd see. So air that you inhale, the oxygen transfers across the grape or the alveolus and into our blood vessel. Oxygen is picked up by red blood cells and is then transported around the body where it is used to make energy. And as a byproduct, we produce carbon dioxide, which we then exhale out. And plants do the complete opposite. Plants take up carbon dioxide and produce oxygen. So we have this mutually beneficial relationship with plants. If you were to take a very, very thin slice of a lung and look at it under a microscope, this is what you'd see. So all of these white holes or white gaps are like the inside of those grapes, and that's where the oxygen is contained. And all of the purple that you can see here is the wall of the grape, and this is where all the capillaries are, those blood vessels. So this, you can see that air is in constant contact with these blood vessels, allowing for efficient gas exchange. And I hope you can appreciate that there's a huge, huge surface area available for efficient gas exchange. In fact, if you were to take a healthy human lung, both lungs out, and spread them out, the total surface area would be roughly the size of a professional tennis court. However, in a disease state such as emphysema, this surface area is dramatically reduced. Now, the number one cause of emphysema is smoking, with up to 85% of patients reporting current and or previous smoking. And if you were to take a thin slice of a person with emphysema's lung and look at it under a microscope, it would look something like this. And I hope that you can appreciate that there are these big holes or big gaps in their lungs. So that all the air here isn't in as much contact with these blood vessels to allow for efficient gas exchange. And the number one symptom of emphysema is shortness of breath. So a lot of these patients find everyday tasks, such as walking to the shop or going up and down stairs, very challenging. And also up to 50% of patients report increased anxiety or depression because of a decreased quality of life. At the later stages of emphysema, what happens is, as you've heard already, high blood pressure can happen or can occur in the lungs because your blood is trying to maintain your heart is trying to maintain a constant level of oxygen throughout the body. However, if we reduce the surface area in the lungs and reduce the number of these capillaries, it increases the pressure in our lungs and puts our heart under a lot more stress and strain. And what happens is these patients develop really high blood pressure within their lungs, which is known as pulmonary hypertension. And currently, there's no cure for emphysema. There's only symptomatic relief, so we can give these patients oxygen therapy, but we can't reverse it. And this is a really big problem because currently emphysema, along with chronic bronchitis, is the 4th leading cause of death worldwide. And it's predicted to be the 3rd most common cause of death worldwide by 2030, so within the next 13 years. And this is due to increased air pollution as well in our global cities. In Ireland in particular, we have a really high rate or prevalence of emphysema, and this is more due to the genetic component of emphysema. So we have really high rates of alpha-1 antitrypsin deficiency, which is the genetic form of emphysema. So how does this all relate back to Lance Armstrong? Well, as I mentioned before, Lance admitted to taking a number of sports performance-enhancing drugs. So he took human growth hormone to increase his lean muscle mass. He took testosterone to increase his strength. He took corticosteroids such as cortisone to stop inflammation after training, so he was able to recover better. But he also took erythropoietin, or EPO. So EPO is a naturally occurring hormone within the body. It's produced mainly by our kidneys, and its normal everyday function is to increase the number of red blood cells circulating in our blood. Now, as I've said before, red blood cells carry oxygen. So if you abuse EPO and you take too much of it, what happens is you increase the oxygen carrying capacity of your blood. Therefore, you don't fatigue as easily and you're able to beat everybody else and win. So this is the normal function of EPO. However, recent research has indicated that it also has this kind of superpower function, whereby it's able to stop the cells in our body from dying. It keeps them nice, happy, and healthy. And it also helps them to multiply or to reproduce. So in the setting of emphysema, where we have a loss of these cells, if we were able to stop them from dying and help the cells that are already there to reproduce and regenerate, this would be a great idea. So why don't we just give patients EPO? Well, if you have normal levels of red blood cells within our body and you take EPO, what happens is your blood thickens and becomes like a jam consistency. And you have increased risks of clots, heart attacks, and strokes. And unfortunately, in the late 1980s and early 90s, a lot of elite cyclists actually died from abusing EPO. They died of heart attacks and strokes. So what I do is I work in close association with a New York-based pharmaceutical company who have taken the good functions of EPO that we want to look at without increasing the red blood cells. And they've called this ARA 290. So this just does the tissue protective functions, all the good stuff. So my PhD then focuses on, well, can we take this drug, this ARA 290 drug, in the setting of a diseased lung and restore a lung back to a normal, healthy lung? So in order to do this, I work with mice. Now, I don't make them chain smoke in their cages in order to develop emphysema, but instead I get them to inhale a tiny, tiny volume of liquid, which eats up their lungs and causes these emphysema holes in their lungs, these big gaps. Once these mice develop emphysema, I then start to inject them with this ARA 290 drug, a small injection every 2 days just into their tummies. And at the end of the treatment, what we do is we humanely euthanize these animals. We kill them under anesthetic, and we then take out their lungs and we section them and we look at them under the microscope. And what we see is that our emphysema lungs, again, have these big holes, these big gaps, indicating that they have developed the disease. When we treat them, though, with the ARA 290, you can see that these gaps aren't here anymore, and it's actually quite comparable to a normal, healthy lung of a mouse. We also looked at the blood pressure in these mice. As I said before, high blood pressure, pulmonary hypertension is quite serious and leads to heart failure, and it's an independent predictor of death within these mice. So when we looked at the blood pressure in our normal healthy mice, they had normal levels, normal pressures within their lungs. However, our emphysema mice had increased pressures, indicating that their heart was under a lot of stress and strain. When we treated these mice with emphysema, though, there was a reduction in this pulmonary pressure. And in a clinical setting, this would be the equivalent of increased lifespan and increased quality of life, overall quality of life. So far in my PhD, I've shown that ARA 290 in the setting of a diseased lung can in fact restore it back to a normal, healthy lung, but we don't know how it's working. So what we think is happening is that ARA 290 is causing the growth of those tiny blood vessels, those capillaries, and that's where my research is focusing at the minute, is to see, can this drug induce the growth of these blood vessels? So I'd just like to thank my research group, all of the pulmonary research group here in the Conway Institute in UCD, and in particular my supervisor, Dr. Catherine Hell, and Dr. Keith Rochford, who is a postdoc working within our lab. And I'd also like to thank Margaret and Craig for organising the event today, and thank you all very much for being here.